Greetings, this is Purple Target from Crash and Learn, and welcome to my tutorial / Let's Play KSP series, Krash Test Kerbals, episode 1 TAC 2 Bravo of Apples and Newton. Currently using Kerbal Space program version 18.2 by Squad. At Crash and Learn we explore just enough rocket science to be dangerous and learn how to abuse math instead of the other way around, to get our Kerbal out into the depths of space, more or less where we want them for fun and profit. So for today's objectives, we're going to be looking at aerodynamic drag, what it is and how to calculate the force it exerts on our spacecraft. Hand in hand with that is how to calculate terminal velocity. And we will look at the KSP drag model and how it computes the drag coefficient that is used in those drag equations. We'll look at the bugs that are inherent to the current drag model and how it doesn't exactly resemble real life. Fortunately, KSP is due to overhaul the drag model in the next couple of point updates, so I'm hoping they will resolve most of those issues. And finally, we'll look at terminal velocity and how it influences a fuel-efficient ascent out of an atmosphere, and why throttling down is often preferable to the max thrust, short burn type of ascent that we looked at when we were taking off in vacuum in the last episode. So you may recognize our heavy metal robot probe from the first episode. This is 1 Bravo. We've just added a couple of stack separators, and we're going to test a free fall of those objects from an altitude of 80 kilometers over Kerbin. So the concept here is, like in the vacuum case, that what comes down should be able to go up. So an object falling through the atmosphere of Kerbin is going to have gravity acting on it during its descent, and that is not going to be exactly equal to, but it will be similar to the gravity acting on the object on its way up as well. Similarly, the drag exerted by the atmosphere on an object falling will be similar to that exerted on an object trying to accelerate up through the atmosphere at about the same rate. Now this version of analysis is just my own insanity. It's not approved for real life, and it's not intended to give us exact numbers that real life situations might require, but it should give us a decent ballpark from which to work from for future estimates. So as 1 Bravo makes its ascent, we'll talk a little bit about the equations of aerodynamic drag and how to calculate the force it exerts on the spacecraft. And then on its way down we'll do a calculation for each second of free fall to determine the gravity at the altitude it's at, how fast it ends up going, the resistance from air drag, and how much it accelerates or decelerates based on those numbers. It's an iterative process because there's a lot of changes going on. We have the pressure changing due to altitude as well as the force of gravity changing due to altitude, so both of these will influence each other. So just find it easier to use a simple case of a 1-ton object falling in 1 second intervals, and then we can add everything up at the end to find out what our total results are. This is one of those cases where it's a really good job for a spreadsheet if you don't want to be sitting there filling out pages on pages on pages of the same calculation over and over and over again, repeat until insane. Get the spreadsheet to do it for you. Anyway, the purpose of having our little heavy metal robot probe go up and do this test is to validate the results. So we'll see at the end of the drop what the results the game produces as opposed to the calculations to see if we're close. And again, I'll repeat my disclaimer, this is just my analysis. No way bears anything that would actually be used. Your mileage may vary. For my next trick today, I'm going to skip over what aerodynamic drag is actually about. I figure it's pretty self-evident if you've ever driven down a highway and stuck your hand out the window. Enough said. So instead we'll skip right over to the less intuitive formula for the force of aerodynamic drag, FA, which equals 1/2 times the density of the medium, think swish your hand through water versus swishing your hand through air, times the surface area, think big hand versus small hand, times the coefficient of drag, think flat hand palm to the wind versus balled up in a fist. It's just governed by the shape of the object, times the square of the velocity, and you can get that from the speedometer of the car. Now for KSP and KSP only, there's this equation for rho, the density, equal to P, the pressure at a given altitude relative to Kerbal standard at sea level, times 1.223, obnoxiously long number, which I think is just the molar weight for standard air, and that's multiplied by 0.008. Now I think this is just a scalar for KSP and KSP only. Wouldn't recommend trying it at home unless you know what it's for. But the indicators from my research seem to be that it's just something that the game does. And calculating the pressure of atmosphere at a given altitude is given by this other equation of P naught, which is a constant based on the planet that you're on. So for Kerbal, that number is 1. For Eve, I think it's like 5 or 7 or something like that. Times E raised to the power of negative altitude over h, which is a scalar height, which for Kerbal is 5,000. Again, that's based on the planet in question. So we'll just run these backwards through a quick example to see how they work. So step 1, we have to find the atmospheric pressure. So P naught is 1 for Kerbal and the scale height h is 5,000. And we will use an example altitude of 11,200 meters. So plugging all that in, we end up with a pressure value of 0.106 times the standard sea level pressure on Kerbal, which if we wanted to translate into kilopascals, we could multiply that by the 101.327 that is standard for sea level, and we would end up with 10.8. Now, if only there was something we could compare that to, an experimental device, maybe something that measured something like the pressure of air around the spacecraft. Kind of like a barometer. Oh wait, we do have those, don't we? I didn't put one on the spacecraft, but I'll leave that for you to do. So then we go to step 2, translate that pressure to the actual density represented by the letter rho. And we'll plug that into the formula, the 0.106, and we end up with 0.001. And probably a bunch of other stuff that we might not actually be seeing because we've plugged all this into our spreadsheet, so it's doing all these calculations very precisely in the background, but we don't have to bother ourselves with them. Right? Now step 3, we plug that into the force equation for air drag, along with the drag coefficient of 0.2 for the part that we're dropping, which is just a stack separator, or really, 90% of the other parts in KSP. Now we can use a surface area value of 1, because then we can basically safely ignore it. I think KSP mostly kind of lumps the idea of A times CD together into the drag value. You can work that either way. And then we're going to use a velocity in this example of, say, some weird number like 688.2 meters per second. Anyway, all that should give us an answer of 49.1 kilonewtons, which fortunately, if we plug that into the mass times acceleration equation, since we're only dealing with 1 ton, the 1 kind of cancels out and we still end up with 49.1 meters per second squared. See? Too easy. So quickly we can just look at the vacuum case as we did in the last episode. How long would it take an object to fall from the parking orbit of 80,000 meters? And what velocity would it have when it hit the ground? This is of course assuming a vacuum, and mostly we're calculating it just to have a comparison against the other values that we're going to calculate here today. Another number that's really handy to have in our back pocket is the acceleration due to gravity at a given altitude. Since we are significantly changing the altitude, the force of gravity will also change over the course of these calculations. So again, for 11,200 meters, our acceleration due to gravity is going to be 9.45. So we'll get our probe up to 80,000 meters and bring it to a stop, and then pop the separator components, and we'll follow those down since they have a fixed and known drag coefficient, and we'll see how it compares to our calculation. So with the rest of this formulas, we can just go through the process of for every second starting from the object at 0 velocity and 80,000 meters. We calculate its descent on the vertical plane all the way to the surface, altitude 0. So to step through this process, we'll take an example at time second 134, just as a for instance to kind of walk through the process. So at the beginning of second 134, our distance or altitude above Kerbin just happens to be 11,200 meters, and the velocity the object is currently traveling at is 688.16 meters per second towards the ground. Boy, isn't that funny? We just kind of calculated the acceleration of gravity at 11,200 meters, being 9.45 meters per second. And it just so happens that we had the exact velocity and altitude values to calculate the force of air resistance too. Anyway, put them together and we get a net force of 39.68 kilonewtons, and that can be divided by the mass, in this case 1 ton, but don't forget to use your mass if you have a ship that looks different. But in this case we can just go straight to 39.68 meters per second squared. And then it's pretty straightforward case of going to the velocity at t plus 1 or second 135 as being our 688 meters per second and adding that 39.68. And similarly for the distance, we can add the altitude that we started at and take away the downwards velocity that we just found, and we get the altitude for second 135 as 10,572 meters. And there we go, we're ready to start calculating everything over again for the values on the next second, and next wash, rinse, repeat until we get to altitude 0. When we get there we can add up all our little g values and we end up with a total delta v exerted by gravity at 1585 meters per second. We can do the same for all the accelerations due to air, and that gives us 1480 meters per second. We can compare that for the delta V for the altitude in vacuum that we originally calculated at 1256. And that starts to give us an idea of what kind of delta V values we would be looking at for the ascent. So just to validate and make sure our equations still make some sense, we can look at our last line item, 183 seconds, when we get to altitude 0 and hit the ground at a velocity of 105.83 meters per second. And we can compare that against the actuals that we get from the HMR-1 Bravo. And survey says 181 seconds and 106.6 meters per second. Close enough for government work. So our previous F-net calculation of force of gravity and minus the force of air drag, eventually an object can go fast enough that that force of air drag ends up equaling the force of gravity, so the net force ends up being 0, and that is terminal velocity. It's that point where the air resistance of the falling object reaches an equilibrium with the force of gravity, and it makes it so that the object doesn't accelerate any faster. And we have this formula here to calculate that. Now note that air drag is not dependent on mass, it's only the surface area and the size of the object. So if we were to get something that's the same size and shape but had 4 times the mass, the terminal velocity ends up being double that of the light version. Think of 2 balloons that have the same size and shape, so they have the same values for air drag, but one is filled with air and the other one filled with water. Which one's going to fall faster? So there's a bit of an issue here with KSP version 18.2 and prior, in that the drag coefficient value is determined by taking the drag value of the part multiplied by that part's instantaneous mass, and then the game adds all those drag coefficients together for each part on the spacecraft. So this has a side effect of throwing an extra mass term into the equation, and it ends up cancelling out the mass from the gravity term on top. And it means that as far as KSP is concerned, all objects that have the same drag value have the same terminal velocity. This basically breaks something to do with Newton, although I'm not exactly sure which law specifically. but it means that spacecraft have no momentum when it comes to air drag. So on Kerbin, an air balloon and a water balloon would fall at exactly the same rate. So we're launching a sounding rocket, tester air drag 1, to demonstrate this concept. And here's the table of values we'd use to calculate the terminal velocity, and as you can see, the empty fuel tanks and the boosters have the same terminal velocity as their full counterparts, whereas in real life the full tanks would have a higher terminal velocity. So TAD1 has a pair of tanks that have been drained to empty and a pair that will remain full when they're finally disconnected at altitude. And we can see that they will move and fall through the atmosphere together at exactly the same velocity, almost the same as objects would in vacuum. Different masses, but exactly the same drag coefficient. And second 5-9, our fuel tanks hit the ground altogether, full and empty. 106.6 meters per second versus our calculated 101.1. And that's promptly followed at minute 4 with full and empty boosters again falling together, impacting at 85.3 meters per second versus the calculated or estimated 82.6. So for the next sounding rocket, TAD2, we're going to take a look at some Nosecones. Some people keep asking if Nosecones do anything, and for now they mostly just add mass. But these particular Nosecones actually have a higher drag coefficient than the regular fuel tanks. So in this particular case, they actually end up slowing the fuel tanks down. And we can see this by adding the Nosecone. It actually ends up adding drag as well as the mass. And we end up with an assembly that ends up with a lower VT than just the tank by itself. So it might be aesthetically pleasing, but at the moment they can actually hinder rather than help, particularly with regards to air drag. We'll just speed things up for a moment while the velocity bleeds off the Nosecone and tanks here. Nosecones with the higher drag, of course, are going to come to a stop sooner, but they're also going to be slower to hit the ground. So you'll see the tanks come by them on the way down. So we can see, as predicted, our fuel tanks hit first. Note their velocity at 107.1 meters per second as opposed to our calculated 101.1. Followed immediately by our Nosecones, traveling at 101.5 meters per second as opposed to our estimated 96.6. The main part here is, of course, that they are still going slower than just the plain fuel tanks, which is consistent with our predictions. Now for TAD 3, I'm going to show something really peculiar. We've already established that full or empty objects with the same drag coefficient fall at the same rate, but spacecraft are usually a collection of parts. So what happens when we combine them? So here we have a girder part strapped to a booster, and two of the boosters will be fired and two are going to remain full when we drop them at altitude. But boosters have a higher CD, so the girders actually make a better nose cone for boosters than those other blue nose cones make for regular fuel tanks. Anyway, because the mass of the girder is fixed, the CD remains constant, while the drag coefficient of the booster ends up getting smaller as it burns out. So the contribution of boosters drag to the sum of the two parts together becomes smaller. And we see here that the empty booster ends up falling faster than the full booster. That's right, the air balloon falls faster than the water balloon. So I don't know how long this video is actually going to stay relevant. squad is aware of the bug and they're planning on overhauling the aerodynamic model anyway over the next couple versions. I'm not exactly sure what the technical issues were involved with the physics engine or Unity or whatever, but I do know that the current model and the drag values are mostly just placeholders for now. My hope is that they won't just rebalance the numbers to behave differently, but I'm hoping that they're able to actually fix this bug entirely. Even if the drag value is scaled to the dry mast but then remain constant, it would alleviate this particular phenomena where Kerbals don't need to get wet in the summer because they can have air balloon fights just as easy as water balloon fights. If there is an upshot to this bug at the moment, is that aerodynamic drag is very easy to predict because it's not contingent on the inertia of the ship. So in terms of predicting air braking altitudes, it actually makes that equation probably a little bit easier because you don't need to know how much fuel you have on the ship when you're trying to figure out how deep in an atmosphere you want to brake. But that's a topic for a much later video. Probably by the time I get to it, they'll fix the drag model anyway and it'll be moot. And we'll just freeze frame here at minute 16 where we can see our empty boosters about to hit the ground at 91 meters per second. We had predicted 87.6. And 2 seconds later at 118 we have our full boosters lazily getting around to the ground at a leisurely 86.3 meters per second, though we had predicted 83.4. So again, our predictions are consistent with the results, where the empty boosters were still able to outrun the full ones. So our last topic today is a fuel-efficient ascent through the atmosphere. Now, as you may recall from the last episode, that the higher our thrust, the quicker we could get up to orbital speeds and minimize our gravity drag. However, when we're working with an atmosphere, things change a little bit because now we have to balance our losses to gravity drag with the losses to atmospheric drag. So when trying to take off from atmosphere, particularly when it's nice and thick near sea level on Kerbin, for example, our optimal thrust to weight ratio is 2. And we want to just push the edge of the spacecraft's terminal velocity on the way up. And that way the spacecraft will reach an equilibrium when it's losing one part of drag due to gravity and an equal part of drag to the atmosphere. As I tried to show here, the efficient case shows X as the delta V lost to drag from each side when the ship is on the edge of that terminal velocity. Now, as we've seen before, if we reduce the thrust, we increase the gravity drag. So let's say we make it so that the average velocity is half as much as before, so it takes twice as long to reach our target. So we lose the 2x of delta V to gravity drag, but we still have some atmospheric drag as well, even though having the velocity quarters the atmospheric drag. This still ends up that we lose more than the optimal case 2x of delta V to drag overall. So instead we have something like TAT4 here, going full throttle as fast as it can, right past terminal velocity. So if, for example, we were to double the velocity in half the time to target, it would half our gravity drag. But doubling the velocity also quadruples the atmospheric drag. So now we're burning our fuel 2.5 times as quickly as in the optimal case to get to the same place, and we're losing most of it to drag. Now don't take these numbers as exact, but it should illustrate the principle and why all the recommendations from longtime KSP players keep saying to follow the terminal velocity profiles. So TAD-4 is just a very simple liquid fuel sounding rocket. It's 2¼ tons with 4 tons of fuel, bringing it up to 6¼ and running on a single LVT-30 engine, giving it 215 kilonewtons of thrust and a thrust to weight ratio of 3.5. So it's very easily able to push itself past terminal velocity, but it can also control the throttle. So we're just running a couple tests here, this one full throttle to see how high it can get, and that will give us an indicator of how much it's lost to drag when we compare this apoapsis to a second flight where the throttle is controlled to try to keep the ship near its terminal velocity. So here we finally have our baseline for a full throttle ascent for TAD-4 of 178,777 meters. We'll skip over the part where this whole thing falls back to Kerbin and has its inevitable meeting with the ground, and we'll go to our second flight where we try to ride the edge of terminal velocity in the hopes that reducing the aerodynamic drag allows us a higher apoapsis than this 178K.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, mark.
So in this flight of TAD-4, we're going to modulate the throttle to try and keep it close to the terminal velocity. So I've gone through a similar process to the free fall calculations, except that I've added in the engine and I'm calculating everything second by second going upwards. And part of that is a calculation of how much throttle is required to overcome gravity drag, and then just enough to keep the acceleration of the spacecraft to keep pushing and sticking right near terminal velocity. So we're able to graph all that out, and we can see here that at about 4 or 5 seconds into the flight it'll reach terminal velocity, and that's when we can reduce our throttle to about 50%, and it mostly stays at about that level up to about 60 to 90 seconds into the flight. And during that period we can start creeping it up back up towards a 100% throttle. It so happens that that time period ties in with the estimation of the spacecraft being up around 12 to 15,000, where the terminal velocity takes off a lot quicker than the rocket is able to accelerate to. Or for rockets with limited delta V, it just may not be capable of going fast enough to ever reach that terminal velocity after that point. So 12 to 15,000 meters is about where you can open up the throttle on just about any spacecraft under the current drag model and carry on balls to the wall to orbit. It also tends to be the altitude that ties in with most people's gravity turns when they can start translating to horizontal velocity, but that'll be the subject of the next video.
Flame out.
So watching map view has given us lots of time to see where our apoapsis is going to be for this second flight. And we can just take a look at our two numbers. The first flight we reached an apoapsis of 178,777 meters at 4 minutes and 43 seconds into the flight, after the flame out of the engine's exhaustion of its fuel at 1 minute and 4 at about 30,000 meters. For the second flight, the fuel lasted till 1 minute 46 and 41 kilometers, and we're going to reach our apoapsis at 6:21 and 244,738 meters. So that can show a difference right there of how much we were losing, mostly to atmospheric drag, as compared to the extra gravity drag between the first and second flights. So I think that just about covers everything we could want to know and more about aerodynamic drag in Kerbal Space Program. I'm hoping that the bugs will be resolved in future versions, but some of the baseline formulas and whatnot should still hold up even after the changes of the aerodynamic model. So I'm hoping only the middle part about the bugs will actually become invalidated after 0.19 and 0.20 come out eventually. And now that we've gone through the whole process step by step, hopefully it's pretty clear that atmospheric drag isn't an overly complicated thing to calculate. It just might be somewhat labor intensive unless you use tools like spreadsheets in order to automate some of the grunt work for you. And hopefully at the very least there's a better appreciation of the why of things, particularly with things like maintaining the terminal velocity when trying to climb your way out of a thick atmosphere. So if you learned anything from this, or enjoyed relearning about something you already knew, or whatever, throw a like, make a comment. It'd be good to know if this is helpful, or if you got a better way of doing things, or a quicker way of calculating. I'm all ears. This has been Purple Target at Crash and Learn. Peace out.